In the 1820s and the 1830s, a guy named Michael Faraday of England was playing around with current. This is back when scientists licked batteries for the fun of it. So if I have a loop of wire here with a power supply and a switch, so that you connect the switch to make the current flow, take the switch off to make it stop. And he had another loop of wire over here connected to an ammeter. He would connect the switch, and therefore a current would start flowing through here. And he noticed that when he connected to the switch, this ammeter, or probably a galvanometer, since they tend to be a little bit more sensitive in my experience, that a needle would flick, that a current was suddenly induced in here. When he disconnected it, on this side over here, the needle flicked in the other direction. And I say flicked, it would go off and then come back. Go the other way and then come back. He played around with it a little bit. He sort of made this skinnier, and it didn't get quite as effective. He went this way, not as effective, moved far away, not as effective. What really was effective was when it was close to here. Matter of fact, if you could actually put this wire inside that. So I've got my circuit, outside circuit here, and then I've got my galvanometer set up there. And that's a hint to a lab that you do later, or watch later. That he realized that what really was the effect, since this was staying constant, what affected was how much of the magnetic field created by this was affecting that. And since the area here seemed to affect how much the needle flicked, he eventually connected this voltage that's induced in this wire right here. This is a symbol for the EMF. This is an ideal voltage. That is proportional to the change in the magnetic flux with respect to time, or calculus space, d phi b dt. The next step, this was 1832, he comes out with that. 1833 and 1835, there's a guy named Emil Lentz, who is Russian, comes out with two papers related to this, and he actually formalizes it a little bit more. Generally, he's credited with the negative sign, but that negative sign is critical, or delta, but the negative sign up front is the key. This negative sign is the part of the model that basically describes why nature hasn't killed us. Let's think about that. This minus sign is telling me that the voltage that is produced is opposing the change in the magnetic flux. So if I connect the wire here, let's look at this scenario in this situation right here. If I connect the wire, I suddenly create a current going in a counterclockwise direction. So because it's going counterclockwise, it is producing a magnetic field that is coming out of the page inside and into the page on the outside. Which means the magnetic field that is going through this loop here with the ammeter is going in. So there is a flux that is increasing in the middle of this going down. The minus sign is telling us is that the current that is produced here wants to oppose that change. And so when I connect it, the magnetic flux is suddenly getting bigger, going down that way. Well, I guess magnetic flux doesn't have a direction, but it wants to reduce that change. And so it's going to create a current that creates the magnetic field going in the other direction. So the current induced, this is the induced current, not inducted, induced current, will be going counterclockwise also, so that it produces a magnetic field that opposes this magnetic field. In this situation right here, when I connect the switch, that I have a current suddenly going in that direction, it creates a magnetic field coming out of the page here. Since the magnetic field is coming out, I have my change in flux is increasing sort of in that direction, and I know the wording is off, but hopefully the spirit is there. So the induced current is going to want to oppose that. The induced current is going to go in the opposite direction here, because it's creating a magnetic field that opposes this external one. So we got these two competing magnetic fields. We have the magnetic field from the outer wire here, or the one that connected to the power supply, and then we have a magnetic field created by the induced current in the secondary wire. Sort of illustrating that a bit more, I have an area here with a magnetic field coming out of the page. From an experimental point of view, we actually can get pretty darn close to this. We can sort of, in a sense, trap the magnetic field to a specific region. And then I take a loop of wire here. So it's not a square, it's just a loop of wire, and the loop of wire is going inside there. I'm sorry, it's sort of empty, it's just 4 wires, or 1 wire shaped as a square. As this enters, suddenly the magnetic flux inside here will be increasing. It wants to oppose the increasing magnetic flux. It has 2 choices. One, it can change the area of the wire, which is not particularly easy, or it can induce a current which changes the magnetic field. So since this magnetic field is coming out, as this enters, as the square enters into the space, it is going to create a current. So when it gets to here, it will create a current that creates a magnetic field going into the page. So the induced current will be clockwise. When the square is completely inside, there's no change in the magnetic flux, and so the current is 0. And then as it leaves, my magnetic flux is suddenly decreasing, so it's going to create a current that wants to bolster the collapsing magnetic flux. And so it's going to create a current, since this is coming out, it wants to create a current going around like that. So this will have a current flowing in that direction. So the induced current will try to either bolster or hamper the magnetic field that is created. All right, actually, the change in the magnetic flux. So the magnetic flux increases, it wants to decrease it. If the magnetic flux is decreasing, it wants to increase it. Let's take it the next step. If I take a bent piece of wire here, and I'm going to make this distance here L, I have a magnetic field that is bathing it. The magnetic field is coming out, so let's set up a coordinate system. I, J hat, and K hat coming out. And on top of this, I'm going to put a wire. This wire is not connected, it's touching it, so we can get a complete circuit here, but the wire is not physically connected, it's just sitting on top. So we start out with this distance here, which we're going to make X, and my magnetic flux is B dot A. My magnetic field, we'll just make B coming out. It's a uniform magnetic field, just to make things not as complicated as they could be. So this is B times A. Let's make my area vector also come up, and so that's just BA, which is B times LX. Now I take this wire and I'm going to move the wire out at some speed V. So now my magnetic flux is changing. It's not changing because of a changing magnetic field like the earlier examples. It's changing because I have a changing area. So my change in the magnetic flux would be the change in BA. Now B is uniform and it's not changing with time, so that stays constant, so this is just B times the change in the area. Well, area is just the length times X, so this is B times the change in LX. But the length isn't changing. The only thing that's changing is this distance here, so this becomes BL times the change in X. So the change in the magnetic flux over time is equal to BL delta X over delta T. And that change in distance over change in time is just the speed. So this is the induced EMF. I'm not worried about sign right now. And this is actually, assuming almost every one of you has seen Princess Bride, and if you haven't seen it, then that is a homework assignment for you, that you need to watch Princess Bride before the end of the summer. It is the perfect movie. But when Wesley is being treated by the Billy Crystal character, and he pumps air into the lungs, what does Wesley say? What does Billy Crystal think he says? Billy Crystal thinks he says, blev. The blev. Princess Bride reference right there. So that is the induced EMF. That is the induced voltage. So we can now sort of make some predictions here. Now, in terms of the direction of the current, that I have, my magnetic flux is increasing because I'm moving this away. So it's going to induce a current that wants to oppose that. If my current runs counterclockwise along this circuit here, then it's going to increase the magnetic field in the middle, which we don't want. So the current is going to be running clockwise, because that'll create a magnetic field going into the page, which is going to slows down the increase in the magnetic flux. If I have a resistor here, let's actually do some numbers here. Let's make this 0.5 meters. Let's make the initial distance here, this is a relevant number, but make it 7 meters. Make this 2 meters per second. Make the magnetic field, we'll make it huge, 3 Tesla. And that's all the information we need. And oh, I have a resistor right here, and we'll make it a 10, no, let's make it a 9 ohm resistor. So I know that the induced voltage is going to be 3 Tesla times 0.5 meters times 2 meters per second. So that becomes 3 Tesla meters squared per second, which obviously is a volt. Now, how do I know that? Because I know this is voltage and the equation has to work. The units have to match. So that's 3 volts. That's going to be equal to the current times the resistance, which is 9 ohms. This is IR. And so the current that's induced is 1/3 amperes, and it is going clockwise. Counterclockwise would be CCW. Recognize that A right there is amperes, that A right there is area. Now it works in more than just this case. So if I have a metal bar here of length 4 meters and I drop it, let's make the magnetic field somewhat realistic. Let's make that 0.4 meters to make it realistic. This is about 0.5 times 10 to the negative 4th Tesla, which is about on par with Earth's magnetic field. And let's say that it's coming out at this moment. When I first drop it, it doesn't have any speed when I first let go, but it does pick up speed. So let's assume it's going at some point 5 meters per second. Then the induced EMF is going to be 0.5 times 10 to the negative 4th times 0.4 times 5. And so that's 2. So we end up with 0.1 millivolts. Now, which way will the current flow, or which is the higher? Well, if I've got this falling, so think about it this way, I have positive charges falling going down, and the magnetic field is coming up. So V cross B means the positive charges will flow this way. But we know positive charges aren't really flowing, so actually electrons will be flowing to the right, which means that the higher potential is on the right and the lower potential is on the left, because positive charge flows from high potential to low potential, negative charge flows from low potential to high potential.